Afternoon, everyone. Welcome to the week 9 of the problem solving session for the course Ultrafast Laser Spectroscopy. As we did in the earlier weeks, this week also we'll be discussing the problems which were given in the assignment and something which are related to that also. And we'll try to solve all those problems, and if you people have any doubts in any of the questions, then we are going to clear those doubts also. So, since no one has joined, we'll just wait for some time, and then we'll start discussing the questions. Okay, so now we'll be starting discussing the questions. So first I'll be sharing my screen. Um okay, yeah. So this starts with the first of all in this session or in this week 9 we had discussed some processes which can be studied using the ultra fast lasers or the ultra fast dynamics. So why are we using ultra fast dynamics, and what are the processes that can be studied, and very minutely that too. These are the things that we'll be discussing. So first I'll go to the slideshow. Yeah. So, uh, among the problems, the first was excited state processes are accompanied by. The options for this question are redshifted fluorescence spectra, good overlap of the absorption and fluorescence spectra, faster decay in the red end of the emission spectra, rise time of the blue of the emission spectra. Okay, so first of all, what are they asking, and what is the this excited state processes? So basically, what is the thing we want to know is, uh, say for any system, this is the ground state of any system, say S0. Now what are the things, like say from after irradiation of light, suppose this system reaches, and suppose not this happens, it reaches to a higher excited state, say S1. Okay, so that I represent it as S1. Now what happens is, if this excited state of the some particular molecule is polar enough, okay, it should be polar enough, then what happens is, there are different changes which are observed in the emission. Okay, now how can we learn that? Say this is the, actually this is a bit blur, but we can just understand the things. So first of all, in the excited state, many the processes, say the fluorescence emission occurs, and what happens before that? Before that, the system absorbs certain amount of energy of particular wavelength, it reaches to a higher state. Now here this can be studied using this picture. See, this is the emission spectrum for any material. Okay, for this material, this was the uh, this is the emission spectrum of, say, the ground state. Okay, now if you take the emission of the excited state, you will see that, or after some time later, you will see that you will get two peaks. The second one, this is a bit, you can say it to be as red shifted. Okay, so this is something which is associated with, say, the excited state of the molecule. Now when you look at this, say, when it comes from this S0, say S0 to S1, it went through absorption. But what has happened, from S1 to S0, it may return by emitting certain amount of wavelength that is equal to h nu. Now, with respect to time, we can say that if we just excite this polar state, then we can observe that the next emission, which has a different wavelength from the initial one, and it is a more redshifted also. Therefore we can also say that in the excited state there is some kind of emission which is of lower energy and therefore is more redshifted. Okay, so in the excited state process, if we take the example of this case, say this is written to be as 325, this is 375, this is 425, this is 475, this is 325, I'm sorry, this is 525 again, and this is 575. Okay, now basically what we want to explain is, if the if we talk about any system, say a molecule, then there may be some processes, there are some processes that are the attribute to the dipolar nature or the polar nature of the excited state. So one of the point to note is the excited state must be polar. Now the another thing that is like, since the excited state, in the excited state, there is a less band or less energy gap between the two states, which leads to the redshift. Acha, okay. We can also say it to be like this. Suppose the ground state was, we can construct it like this diagram. So with time, what happens? Uh, the excited state processes. Uh, it happens to be like this, and therefore the emission becomes a little bit of, say, of higher wave number or the less energy. Okay, I think this is not the, it's better not to understand by this, but the earlier one was quite a bit okay. So the excited state processes, they are accompanied by, first, the redshift of the fluorescence spectrum. Redshift in the fluorescence spectrum. Now, basically, according to there is one more rule which that is the Kasha's rule, which states that suppose for a system, say from V is equals to 0 to V equals to 1, or n equals to 0 to n equals to 1, the absorption occurs. Basically, the emission also occurs from the nearest excited or the first excited state to the ground state. So this is the rule that is followed by Kasha's rule. By That is also called as, sorry, that is also called as the Kasha's rule. Now another thing is, if suppose this excited or the excited state is a polar state which has certain amount of lower energy compared to that of the uh, non-polar state, in that case what happens that the two, absorption and emission, which could be like the mirror images of each other, they are not so, and there is some difference, and these processes are called the non-Kasha's process. And in this case, there is not a good overlap between the absorption and emission. Okay, now for this option, what we can say is, for the excited state processes, there is not a good overlap. Okay, between the absorption and the emission spectra. Okay, so what you can say is, for Kasha's processes, or the for if the absorption and emission is according to the Kasha's rule, then the absorption and emission will have a, then absorption and emission will be like mirror images of each other. But in the other case, you will not obtain so. The example for this is shown in this spectra, which shows that in this case, the, say this is the normal emission where the excited state does not occur, or the excited state of the molecule does not happen to have another interaction. But in this case, the excited state has certain uh, uh, he has certain shift which is responsible for the emission at a higher wavelength. Now, there is not a good overlap between the absorption and fluorescence spectra. Then the second is faster decay in the red end of the emission spectra and rise in the time of blue end of the emission spectra. So how can we explain that? Suppose your molecule undergoes some processes. In that case, we can study this through the fluorescence decay curve. Now how is it done? Say this is the decay of the say this is the decay of your say the ground state, and this is the decay of the excited state. Now what happens in this case is, see, sorry, or this is the decay of this emission and this is the decay of this emission. Now if it is associated with some sort of a different process, then what happens initially in this case at time 0, like it will decay instantaneously without any problem, like this shows the dotted line. Now suppose it is accompanied by any dipolar state, so in that case how the fluorescence decay will occur? This decay is distributed into two groups. Okay, so some population will be in this state while the other will be in this state. Therefore the decay for this, or the count for this decay for this emission will reduce, while in this case the red one shows that the red line is shown for this decay, this fluorescence decay. Okay, so basically the blue end of the spectrum, the peak that corresponds this one, the peak this one, it has a decay curve that has reduced in intensity due to the distribution between these two curves. Okay, so what will happen? The decay curve for this A, the decay curve for this A will be somewhat, say, uh, decrease in intensity, while the red shifted, or the one on the red hand side, will increase, or there will be rise in the um, decay curve. Okay, why is this so? Because with the function of time there will be more population that will shift from this say this higher state to this lower energy state. Now what happens? Because of this population distribution between these two states A and B, when the emission occurs from this, the decay of this fluorescence curve will experience some decrease in the count, and the reason is lower population or the population distribution, or population distribution between A and B. Okay, okay. So because what excited state processes are often accompanied by redshifted fluorescence spectra, good overlap of absorption and fluorescence spectra, and faster decay in the red end of the emission spectra, rise time in the blue of the emission spectra. Once again, I'll try to repeat and help you understand. So, what happens in the normal molecule, say with a ground state and an excited state? Under the normal condition, when the excited state is not a polar or is not a polar one, then what happens? Directly from the absorption, emission occurs. So this is a normal condition. Now there may be another process associated with this, where the excited state has a bit lower energy due to the polarity. The more polar it is, the more stabilized it will be, and therefore due to this lower energy of the band, you will notice apart from this, or there will be a new band arising due to the polar nature, where the emission can occur from this part of the band to this. and since it lies at a lower energy, it will be the red shifted one. Thus, because of the polar nature, you will observe that there will be two peaks coming in the emission, which can be seen like this. So this is something which indicates that there is some excited state. Like the excited state is a polar one, and there are certain another process associated with the emission, or with the with the fluorescence emission. Now in the first case, what you will see, say the absorption occurs somewhere from here, at around 388, the emission will be around say 400 or 450 or 488 nanometer. Now in the second case, or if or the absorption and emission will be at the same value, while in the other case, say in the other case, there will be further a new peak arising, which is at a higher wavelength value, and which can be shown as this, shown in by this blue line. And if you study the fluorescence decay of each, you will notice that for this the line at the blue end, or for this band at the blue end, there will be decrease in the there will be decrease, or it will undergo a faster decay, but there will be rise in the decay of the red shifted one. Okay, so this one corresponds to the B, this corresponds to the A. And why is this difference in the A and B? If there is a new state or new process happening, then in this case, because of this kind of emission, the population becomes distributed between two states A and B. If the emission occurs from A, the population it is a bit reduced, and therefore it will the decay will happen faster. While since the population of B has increased to some extent with the function of time, the decay in case of B will be at say, first of all, higher wavelength, and the second thing is, it will also there will also be rise in the decay as a function of population of that state. So the answer to this question is faster decay in the red end. This is not the right option. Rise, oh sorry, faster decay in the red end, and the rise time of the blue of the spec. So actually this is not the right option. Okay, this you could be faster decay of the blue emission. So for this, the answer would be faster decay in the red end of the faster decay in the blue end of the emission spectrum. Okay, let's just see. Yeah, this is the right. Wait a second. Yeah, so actually both of the options are wrong. Why? Because there will be wait. I just thought that the options are not right, but the options are right. So in the red end of the emission spectrum, faster decay will not occur. Faster decay will occur in the blue end. So this will be the right option to this question. Faster decay will be observed in the blue end, and rise time will be observed in the red end. Therefore, the only correct option will be the red shifted fluorescence spectra. Okay. Here also, we can write it as it will have a faster decay, and it will have increase in or rise time. Okay. Now if you have any doubt in the question, or else we'll move to the next question. Basically, this is fluorescence decay curve is normally recorded according to, say, this is your system, which is the pump probe experiment. In this, what do you do is, say this is your system, okay. First of all, you excite it with a pump light of particular wavelength. Then what you do in order to study the fluorescence decay, you again incident it with a probe light. Now what happens when you study the decay of this probe? Initially at time 0, what was the only thing? That was the ground state. Now when you go on with the time, you will see that the decay happens and it changes with respect to time, and second, for the excited state you will note the decay. So basically what how is this fluorescence decay curve recorded? This is recorded using the pump probe experiment which we studied earlier. Now we'll go to the next question. For the first question, we have solved this, and the second question is the value of time constant for the fastest possible reaction at 400 Kelvin according to the Irving equation is. Okay. So first of all, we have to calculate this. The second thing is what they are asked. What we want to know is what is Irving equation. So this is what we had discussed is according to Irving equation, the value of K, which is the rate constant, is equal to KB into T by H Q star upon QA into QB into e to the power minus EA by RT. What all these constants mean? This KB stands for the Boltzmann constant, T stands for the temperature, H for the Planck's constant. The Q is the Q star upon Q into QB is the partition function, while this is the other exponential function which includes the value of activation energy. Okay. Now, the value of time constant, the value of time with respect time constant with respect to the, yeah, the value of time constant for the fastest possible reaction uh, at 400 Kelvin will be. So if you do all the calculations, say for the fastest possible reaction, you need to keep the value of say e to the power minus EA upon RT. You need to consider it as if the reaction is the fastest, then value of activation energy is somewhere 0. Okay. The lower is the value of activation energy, the fastest will be the reaction, right? So in this case, what you can do is, yeah. So in this case, what you can do is consider the activation energy to be 0. Basically, if you consider EA to be 0, the value of e to the power minus EA upon RT will turn to be 0. Okay. And if this, the value of e to the power minus E upon RT, e to the power 0 will turn to be, sorry, it will turn to be e to the power 0, and then the value comes to be 1, right? Then, so this would be written as e to the power minus 0. Okay. And what is the value? E to the power minus 0 by RT. And therefore, it will be written as e to the power 0, and the value for e to the power 0 is 1. So, this part of the question is solved. Now, we have considered it to be 0 for the fastest possible reaction, since for the fastest possible reaction, the activation energy should be the least. If you consider it to be the least, it can be 0, and if you substitute the value of EA to be 0, this whole function turns to be 1. This is the partition function which relates to the A and B, the population, and therefore for this value also we consider that the value of Q star upon QA into QB is equals to 1. Okay. So this also will consider 1. Now K is equals to KB into T by H into 1 into 1. Right? Now I'll just rub it so that it becomes more clear. Yeah. So now when you do the following operation, what you will see, they have asked you to solve at for the value at 400 Kelvin. I'll take a fair page where we can write first the equation where K is equals to KB into T by H Q star upon QA into QB into e to the power minus EA by RT for the fastest process activation energy. Say the EA is equals to 0. Therefore, for the value e to the power minus EA by RT, it will come to be e to the power 0 by RT, and then anything e to the power 0 is equals to 1. Second, first thing is done. The second is Q star upon QA to QB. We take it to be 1. Okay, with the maximum value. Then third comes final equation. Final equation is K is equals to KB into T by H. Here we know all the things. KB is equals to Boltzmann constant. T is equals to temperature. And H is equals to Planck's constant. When you solve, so what you will get? KB is equals to 1.38 into 10 to the power minus 23 joule per Kelvin multiplied by T. T, what are we given here? T is equals to 400 Kelvin. So here it comes to be 400. Its unit is Kelvin. And then what is the value of this? 6.626 into 10 to the power minus 34 joule second. Okay, this is not C, this is second. Joule to joule will be cancelled. And then when you solve this, what you will get the answer? Let's check for a second. So it comes to be 83.3 into 10 to the power minus 23 plus 34. Right? So what will be the answer? 83.3 into 10 to the power 34 minus 23, it comes to be 11. Okay. And what is the unit? Second inverse. Now, what they have asked me to calculate, they have asked us to calculate time constant. So, we'll just take the reciprocal. Since we note that the K is inversely proportional to T, we'll just, and its unit is also second inverse, we'll just do 83 point reciprocal. We'll just take its reciprocal. So, it will be 1 divided by 83.3 into 10 to the power 11. Okay. So when you divide 1 divided by 83.3, so it comes out to be 0.0120 into 10 to the power minus 11, right? Now when you write it, it can 1, 2, 3, 4. So you can write just 120 into 10 to the power minus 15, right? And when you convert this, it has a unit of seconds. It has second inverse. So it also comes to be second because we have taken the reciprocal. And so far, since we know that 10 1 femtosecond is equals to 10 to the power minus 15 seconds. So therefore, it comes to be 120 femtoseconds, right? So the answer to this question will be 120 femtoseconds. Okay. So what we did is first, uh, considering the Eyring equation. So here also I'll write this equation which we have written. This is the Eyring equation. Okay. And using this Eyring equation, we had to calculate the time constant for the fastest possible process. Now, there are three factors which are left at last. First, we consider that let the fastest process be the one which has activation energy 0. If the activation energy is 0, from this equation, this term comes to be 1. The second thing is, say, the partition function for the excited state, we took it to be 1 again, because this is also the maximum possible value of that. Now this turns to be 1, this turns to be 1. What are we left with? We are left with kBt upon h. And what we can say is, this k, the rate constant, depends on the value of t, because the other two are constant. Now say, suppose I say, for now, for our case at present, we have taken T to be at 400 Kelvin. But suppose we calculate this, the same value of rate constant at a certain lower temperature or a higher temperature, then this value will change. And again, if we want to calculate the value of rate constant, then we can just substitute the value of each of this constant and temperature. And when for the temperature T is equals to 400 Kelvin, T is equals to 400 Kelvin, if we are asked to calculate, then the answer comes to be, say, um, K is equals to 83.3 into 10 to the power 11 second inverse. Since they have asked us to calculate the time constant, what we did is, we just took its reciprocal, and it turned out that the answer is 120 into 10 to the power minus 15 seconds. When you convert the same to a lower unit, that is femtoseconds, it comes to be 120 femtoseconds. Okay. Now suppose this is for 400 Kelvin. Say we want to calculate for 300 Kelvin. So the same thing we'll do. We'll just do 1.38 into 10 to the power minus 23 into 300 whole upon 6.626 into 10 to the power minus 34. The total unit for whole is second inverse. Solving all the problems, what you will get is, yeah, then the answer would be 62.48 into 10 to the power 11 second inverse. And when you calculate the same answer, what it will come to be? It will come to be, in this case, I'll just write it with the blue color so that you are not confused. Yeah. So 1 upon 62.48 into 10 to the power 11 comes to be 160 into 10 to the power minus 15 seconds equals to 160 femtoseconds, right? So as we reduce the temperature, the value of rate constant reduces and the time constant increases. Okay. So this is in all. for this question. If you have any doubt, then just ask. Just feel free to ask. First of all, what is Irving equation? So basically, there are two things to remember. First is what is the Irving equation. If you are asked to calculate the fastest reaction, you will just substitute the values, taking activation energy 0 and partition coefficient 1. Doing all this, just substitute the value of all the constants and you can calculate the value of K, the rate constant. Okay. And uh, what what is this? Femtoseconds refers to 10 to the power minus 15 second, and that is it. Okay. Now, for the first question, we discussed about how the excited state processes are related with the change in the fluorescence spectra or the difference in the emission of the any molecule as compared to the ideal case. And how can it be studied? By the emission spectrum, if the by the fluorescence decay curve. By the emission spectrum, you will see a new peak arising that is quite redshifted, while in the fluorescence decay you will see that compared to the original, or say the black line in the way, where is the ideal case. In the case of excited state processes occurring, the decay will be faster one, and the okay, so in this case the decay is faster, right? So I pointed out at the wrong arrow. This is a faster decay, and in this case also a new peak will arise. Basically, this is for the original compound without any excited state process occurring. So I like the now we can correct it, that this is for the original one while this is for the excited state. As you can see, it has a lower, or it has a decrease in its intensity and also has a fast. The question 3 is, in the experiments of Zewell, the bond breaking time and period of oscillation between the bond dissociated and bonded states are respectively. Basically, see, there are many fast processes. Okay. One among the fastest that we used to know is the acid base reaction, that is called to be as the fastest or is the fastest process. So, in the experiments of Zewell, the bond breaking time and the period of oscillation between bond dissociated and bonded states are respectively. Basically, in the Zewell experiments, there was a study that was done on, for the simplest molecule, how much time it takes for the bond to break. Okay. And second thing, what is this period of oscillation for the dissociated and the bonded state? It is shown that when a molecule dissociates, it is not only it does not only dissociates completely and gets separated. It is in the form like, while it gets dissociated at a certain point of time, like there is an oscillation between the bond dissociated and the bonded state of the two. Okay. So first we'll be talking about this bond breaking time. What did they do and what happened in the experiment? So they had taken the molecule that is the ICN for studying this dissociation. So initially this ICN, it absorbs somewhere in the range, say, uh, 280 or 250 nanometer. Okay. Now, now what happens when you introduce or you incident a pump light of 306 nanometer to it, it will reach to a higher excited state. And meanwhile, what did they do is they see there is some population as a function of time in this excited state. Further, they again incident it with a probe light that had a frequency of 388 nanometers. Okay, what is the purpose of doing that? With the function of time, say at time equals to 0, the ground state, the population is at ground state, and basically absorbing a 306 nanometer of light, it reaches to an excited state. Okay, at this excited state, further they what they did, say the excited state is ICN, the bond distance is also increased. With this excited state population, they again excited with a probe light. When they excited it with a probe light, what happened? The population of the excited state again got further excited, absorbing this 388 nanometer. Because of this excitation, the bond is, say, dissociated into I and Cn, and therefore this is the population of this is the emission what you get, or the fluorescence you get, is because of the emission by this Cn star, which is dissociated. Okay, now, how is this photo dissociation studied with respect to time? Say at time 0. See, in this whole process, the fluorescence emission is only because of the emission of this Cn minus. Now, with respect to time, what you will see at time 0, say most of the population from this excited to this. Meanwhile, after some time, when you incident simultaneously with a probe light of 388 nanometers, slowly this Cn reaches to a higher to an excited state, that is Cn star, and therefore the emission will increase. Why? Because the most of the Cn star which reaches to the excited state, it has now started undergoing or giving out the fluorescence, and therefore the intensity with respect to time at time 0 will reach to a maximum value, and further it will become constant. Okay, and like the time which it takes to reach a maximum value, this is the time in which it the photo dissociation has occurred. That is, from ICN in the excited state, the Cn has totally dissociated to Cn star. Okay, and thus when they calculated out the time of this whole process, the bond breaking time, they came out to be 205 femtoseconds. What we want to say is, as we had discussed earlier, fastest processes are somewhere in the range of femtoseconds, right? Now, what they did in this process is they used the pump and a probe to excite the system. Further, they excited the excited state by a probe light to get the dissociated state. So, in this overall, the decay curve as a function of time, or not a decay curve, the intensity curve as a function of time shows initially increase in fluorescence intensity, which then becomes constant. The time required to reach maximum value of intensity is the dissociation. And what is dissociating? Dissociation is the bond dissociation time. Okay. Now, this part is over. What have they asked? The second thing is the period of oscillation between the bond dissociated and the bonded states are. Basically, this is another experiment which the same group had done, in which what they did is, first is the, say this is the NAI. Okay. Now, in this, with this NAI, initially when they excite it to certain, with certain frequency of light, it reaches to the excited state Na plus and I minus. Okay. Meanwhile, this curve also overlap with somewhere the Na curve or the Na potential energy curve. What happens is, when you excite it with light, some of the Na plus it gets converted to Na. Okay. And what is the meaning of this conversion is, this Na plus and I minus, which used to have an ionic bond, now slowly this some amount of this Na plus has converted to Na, because of which you will also see there is the absorption of Na. Okay. And when you see there is absorption of Na, you will see that it's not like the absorption is with respect to time, it's like a single curve. It is like, say, in the form of vibrations, or say oscillation is happening. What does this signify? This signifies that when initially you incident it with a light, say from the ground state, it reaches the excited state, and if you just construct the potential energy, it is not a single level, it is, there are multiple levels. Now when the emission occurs, each of this level 1 2 3 4, they just get converted, and therefore start absorbing. Now each of this is not a single one, they just form a wave packet. Okay. And this wave packet is sought to said to have a periodic oscillation. Why? Because say this whole setup just first of all, uh, comes into two states. The first is when the two are closed in the form of ionic, while in the second state, the Na plus is converted to Na, that is, they are in the bond dissociated state. And finally, after some time, you will see only Na absorption occurs, and slowly the Nai absorption reduces. Okay. So within this period of time, this period of oscillation, they can calculate. And with this period of oscillation, they can also conclude that the bond breaking does not take place at the instance of time. It is a matter of time where initially the bond breaking and the bond breaking and the formation of Na, these two occur periodically, and therefore, or the bond dissociated or the bonded states, they occur periodically, and you get this wavy structure. Okay. And when they calculated the time for this oscillation, the period of oscillation for each, the time came out to be 1 picosecond. Okay. So through this we have just taken a recap of. So with this experiment of Zibel, there could be two things concluding, that is the bond breaking time and the period of oscillation. So with the time when, okay, as a function of time, when the experiment was done on the variety of molecules, especially the simplest kind of molecules, for which each thing could be determined quite accurately. So they could calculate that the bond breaking time, that was 205 femtoseconds. And how could we calculate that? They could calculate it using Wait a second. They could calculate it using the ICN molecule, how the dissociation in the ICN occurs. Why is it called photo dissociation? Because the dissociation is happening as a function of light. Then okay, the as a function of absorption of light. Then second thing, by the studying the bond breaking phenomenon, what we got to know is that the NaI bond does not break immediately. It takes some, it undergoes a period of oscillation where the bond breaking and the bonding states, they have, like, the system oscillates between the two forms. Finally they break, and you say that the absorption turns to be zero with the time, with the function of time. Here, this is the ground state energy. It is excited to this further higher state. Okay, and when you talk about this Na state, there is, say, overlap between the two. This overlap brings that some of the Na plus will be converted to Na, and when this Na plus is converted to Na, say there the two, what you get is a wave packet and which oscillates between these two. Okay, so for the first case, the bond breaking time, that is calculated as 205 femtoseconds, while the period of oscillation between the two, which could be calculated by the difference between these, came out to be 1 picosecond. Okay. Now, what we'll come to the question number 4. If you have any doubt in any of these questions, you can ask. In the first question, we had discussed what are the excited sorry, how is the excited state process, and what are the changes that will be observed in the decay or the absorption or the emission for the excited state processes. One point to note is, even for the excited state, the absorption for the same molecule, the molecule will be the same. The only thing that you will note a change in is the emission spectrum and not the absorption spectrum. In the second case, how can you analyze that there may be a polar state or the polar excited state? You can see that there will be a new peak coming. Second thing, you will note in the decay curve, you will see for the initial molecule, compared to that there will be decrease, or the system will undergo a faster decay. And second thing, there will be rise in the, there will be a new decay curve that corresponds to this second state, and which has a rise in intensity as a function of time. The time here mentioned is in the is a function of nanoseconds. While using the same decay, you can also calculate the lifetime of a particular state. This is what we are calculating in this figure, or we can calculate. In the second thing, we question, we calculate that the time constant using a simple equation. That simple equation is this Eyring equation. If we are given to calculate the fastest possible reaction, considering that the activation energy will be zero and the function of temperature, with the function of temperature, this k will be varied, keeping the value of all constants. You can just, and keeping the value of Ea to be 0, and also the partition function to be 0, you can calculate the value of k, which is the rate constant in the unit of centimeter inverse. Now, if you are given to calculate the time constant value, you can just take the reciprocal of that, and therefore you will get your answer. Here in this case, we got our answer to be 120 femtoseconds for temperature. For temperature is equals to 400 Kelvin. While for the same, just for a matter of trial, we calculated the time for T is equals to 300 Kelvin also, and we found that the time comes to be 160 femtoseconds. While we also noticed that as a function of T, the value of K for a lower temperature is 62.48, compared to the one at 400 Kelvin, it came out to be 83.3 into 10 to the power 11 second inverse. Okay. Now, for the third question, we discussed what was the Zivel's experiment, where he did where the group did discuss that how you can study the bond breaking and the bond like the bond breaking time or the dissociation time using this. And one of the two examples they had done was the photo dissociation of ICN, where ICN is a simple molecule with I plus CN minus. Here in ICN molecule, when you excite it with a light, 306 nanometer, it excited to a higher excited state, where some of the population was further excited to 300 with 308 nanometer of light, which led to the dissociation of bond to Cn minus. This Cn minus then and then shown a process that is the laser induced fluorescence, LIF. And also the when you see the function with the function of intensity as a function of time, then the intensity increases and then reaches to a maximum value at some time. When you calculate the value of this, the time it takes to reach maximum, this time is equal to the photo dissociation time, or it is equal to the time it takes for the bond to break. When they calculated out the time, that came out to be in the range of femtoseconds, since we considered that the bond dissociation or the bond breaking or say the acid base reactions are one among the fastest reaction that take place in the time range of femtoseconds. And when they calculated the same, in this case also it came out that it has a value of 205 femtoseconds. Actually, this is quite a short time, and therefore the process is quite faster. Then they also did the snapshots of bond breaking, and using the same picture we could observe many things. The first is, with the function of time, the NAI absorption drops to zero. Why is this so? Because soon the NAI, after absorption of certain, most of the Na plus that they gets converted to Na, because of which you see that as a function of time the Na absorption reaches a maximum value. Then again, what is happening here is actually this ionic species, since it is converted into Na, we can also call it as the Na and I, and the bond breaking occurs. Since the Na plus converts to Na, and the separation occurs between the two. As a function of time, you will see that there is certain period of oscillation where the whole system oscillates between two states, the bonded state and the dissociated state. And normally if you study the dissociation, no, we cannot observe that certain these processes are also associated with bond breaking. We got to know the same bond breaking picture only through this ultra fast process study, and which is in the further shorter range, that is in the range of picoseconds. Okay, now we'll go to the next question, that is the question number 4, regarding which is regarding the mechanism of the acid base reaction. Regarding the mechanism of acid base reaction proved by the pump probe spectroscopy, the higher concentration of solvent molecules leads to. Okay, now the mechanism of acid base reaction, as I told previously, the acid base reaction is the fastest reaction. Okay, are one of the fastest reactions. Now, earlier they thought that studying the fastest reaction can be can be studied through the ultra fast processes. But when you go on to a higher level, or higher level means when you see at the microscopic level within a system, there will be many factors that will be associating this reaction between the acid plus base. Okay, now when you study this when you study this acid base reaction by a pump probe spectroscopy, initially in this experiment, in order to study this experiment, they had taken two molecules, which this work was done by this neighboring group. And what they noticed is, say they have taken a pyranine molecule which acts as a photoacid. Photoacid means in the presence of light the acidity of the system will increase, and therefore this written as OO, it appears to be OO, actually this is OD. The only thing to notice, the proton in this is replaced by the deuterium atom. Okay, and when this when you study this whole process, you will notice that as a function of time on increasing, or sorry, on incidenting or on, yeah, on when the system is when the system absorbs certain amount of light of particular range, then you will see that this slowly this o and this a separates from d, and therefore, or say this photoacid dissociates, this d goes on to the acetate anion, and therefore you will find the formation of od as a function of time. And this is called the photobase, and this is called the photoacid, while this is the conjugate base, and this is sorry, this is the conjugate acid, and this is the conjugate base for the same. Now, for the acid base reaction, if you study it by a pump probe spectroscopy, let's take a quick revision within 1 minute for this. Say this is a system. Okay, I am representing it as a system. Why? Because say this is a molecule. Initially, you incident it with a pump light of a particular wavelength, as we did earlier in this case. Say this was of 306 nanometer, this is of some other range. Now, what you are doing is, say if you incident it with pump light, as a function of time, at time 0, the system will be at ground state, or soon after absorbing the light, or say the pump light, it will reach to an excited state. Immediately when it reaches to an excited state, you tune it or incident a probe light to it which is perpendicular to it. Now what happens is, apart from pump light, this probe light, the emission spectra of this probe light is recorded. When you record the emission, you will see as a function of time, at time 0 you will not see any emission, but with when the time increases, slowly there is increase in the emission. This is what they had studied in this acid base reaction. Okay. Or when they studied, so they observed that the two concentrations were noted. First is of the photobase, and the second is of this acetic acid, which is formed the deuterated acetic acid, say CH3COOD. In this case, the signal or the intensity, the with respect to time, what you will see, for the photobase and photoacid conditions, suppose, since it is a fast reaction, what you will see, this d dissociating from o will immediately go to CH3COO minus, and therefore will form CH3COOD. So in an ideal condition, in ideal condition, it may happen that the rise in intensity of both photobase and CH3COOH acetic acid are uh, similar, but in normal situation, photobase forms faster than acetic acid. Or say with the function of time, say this is 100 picoseconds, so at function of time, say the signal intensity of acetic acid is only this much, and the intensity of photobase is quite higher. Why has this happened? When you study the dynamics, you will see that in a system, say this is the solvent, there can be, these are the solute particles or solute molecules. When you talk about this pyranine, say photoacid, say this is A and this is B. Okay, these, or this is also an A, this is B, this is again B, A, like this. Okay, they are within the system. Now, because of say the interaction with the other molecules in the solution, there may be a time lag between the two. Say the A has converted to this photo base, but meanwhile this acid has the deuterated, or this D plus ion is not transferred to the B. It takes some moment of time. Because of this, when you measure the signal for A, it comes out to be higher as a function of time. Compared to that, the photo base, its increase takes place sometime later. Now, this whole phenomenon is also related to concentration. Now, it is quite obvious that in a higher concentrated medium, these whole will be close to each other. Say you will find more A, more B, which are close to each other. If they are close to each other, immediately an A acid will find will convert will not to get confused here, the A is the photo acid, the B is the CH3CO minus I am talking about. Okay. Now, in a concentrated system, it is quite obvious that this A will transfer the D ion, cation to B, because anyway it will find some B nearer to it. In this case, this transfer is faster, or for the higher concentration of CH3CO minus in the medium, the A will get more B to transfer to, and therefore you will get the signal which is similar to B. This is for high concentration of CH3CO minus. Now, for the low concentration of CH3CO minus, it will be difficult for this A photoacid to find a B. Not very much difficult, but quite a bit more difficult compared to the first case or the B case. Because of this lower concentration, the photo acid, the this is not photo, yeah, sorry, yeah, this is photo base only. Because of this condition, the photo acid takes some time to photo acid converts to photo base, but through the chain of events that is happening due to the neighboring molecules effect, the CH3CO minus will take some time to convert the CH3COD. Therefore, the signal in this signal with respect to the pulse delay time, you will see that the intensity of the red one, that is the photo base, increases immediately with time. It has no change most of all, but the change but with the concentration of this acetate anion, you will see the concentration of this acetic acid is also affected. Okay. So first, the options for this question were given to. First, we have discussed what is the mechanism in a short way. Next, what they have asked, now we can easily get the answer to this question. Regarding the mechanism of acid base reaction proved by pump probe spectroscopy, higher concentration of solvent molecules leads to no change in the rate of reaction, increase in the rate of the reaction, decrease in the rate of reaction, or first increase then decrease in the rate of reaction. Okay, so here they are talking about the solvent molecules. If the solvent molecules are high, means the solution is dilute, right? And if the solution is dilute, say in say the solute. Okay, yeah, so if the CH3, if they are asking that and they have given a medium of CH3CO minus, then we can also say that it will increase the rate of reaction. Not the solution is dilute. Say the solvent molecules are CH3CO minus. If they are higher, there will be increase in the rate of reaction. Okay. Now, the next question is, if you have any doubt in this question, you can ask, or else we'll go to the next question. Yeah. Okay, so we'll go on to the next question. Here, if they talk about the solvent molecule, since the medium has CH3CO minus, the acetate anion, these are the solvent molecules. Okay, so you cannot call that the solution is dilute. Here, you can learn or the understand in terms that the CH3COO minus concentration is increasing. Okay, or it is increased, right? Now we'll go on to the next question. That is this one. The dimethyl aminobenzonitrile DMABN. Actually, these are the properties written for DMABN. So, what is this say? How can we draw the structure of this? Dimethyl means the N has CH3 groups. Dimethyl amino, and benzonitrile, that means the benzene has a CN group. Okay, now so far what we can understand is this N has is the positive N end, and this Cn has the negative end. Therefore, this is a polar molecule. And for the diaminobenzonitrile, the dual emission is observed in all the solvents. Maximum of the Stokes shifted emission band is polarity dependent. The position of the maximum and the locally excited band is the position of maximum of the locally excited band is polarity dependent. The height of the energy barrier of the excited state is viscosity dependent. Okay. So here I have just kept a graph for your reference, which we they had also discussed in the uh, week the lectures. And if since it is not clear, this is a centimeter inverse, and say this is in the increasing order of centimeter inverse. Okay, so not to be confused, this B band, this B1 or the B band is for the DMABN. Okay. Now there is one process that is associated with DMABN, which is widely studied, is that is twisted intramolecular charge transfer. That is, in the normal conditions, if you say that the molecule is polar, say like this, in the excited state condition, sorry, the molecule is not polar, the molecule is planar. In the excited state condition, it will turn out to be like this. Say it is perpendicular to it. Okay. The two have an angle of 90 degree. Okay. And with this twist only, charge transfer occurs. So this is something which we were talking about, the in the excited state what are the processes that occur. So because of this excited state, the charge transfer is happening in this case of system, which can also be given as, say, in this case, because of this charge transfer state happening, and because of this state only, you notice that, say, this is the ground state and this is the excited state. As a function of polarity, the excited state, it reaches or it becomes it turns out to be at lower energy, or it gets more stabilized because of the polarity of solvents. Here maybe the diagram or the sketch is not bit more clear. Wait, I'll draw it again. Okay. Yeah. So, learning from this spectra, which is the emission spectra, although normally emission which we study in the increasing order of wavelength, here it is in increasing order of wave number. So, therefore, we can also say that this is somewhere it is higher energy transition, and not transition higher energy emission. So in this case, this is the higher energy, this is the lower energy. Basically, if you want to state, say this is for the ground state and this is for the excited state. The excited state becomes more stabilized in the presence of a polar solvent. Okay, because of this, say the emission which could occur like this, now the emission is happening from the excited state to the ground state, and in the form, say, at a higher wavelength. Okay, the same is observed in this case, or a lower wave number. So because of this polarity, or because of this twisted intermolecular charge transfer, that too in polar solvents, becomes stabilized. The more the polar medium will be, the more stabilized the excited state will be, and because of this stabilization, it the emission will shift to a lower frequency or wave number. Okay, now here, in our case, say this is for the at time equals to 0. The more you, or say for the different solvents, say 1, 2, 3, and 4, you will notice for the first case the line goes like this. Okay, it goes like this and it moves and just reaches the ground. In case of B, in the case of second, as the polarity is increased, you notice that it goes like this. Further, in the case of 3, as the polarity is increased, it goes like this, while in the most polar solvent you will find two peaks. Okay, so this is how you can see the picture. The in the diamino benzonitrile, actually this molecule of is of interest. Why? Because this was one of the first molecules in which this process was noticed. Further, there are many molecules that lie in this category where we can say that there is some TICT, that is twisted intramolecular charge transfer happening. Okay, so for diaminobenzonitrile DMABN, the dual emission is observed in all solvents. No, in all solvents that does not occur. Only in polar solvents it happens. Okay. The maximum of the Stokes shifted emission band is polarity dependent. Yes. So the maximum, right, which means that this of the Stokes shifted refers to like it is shifted to a lower wave number, depends on the polarity. So yes, this is the right option. Then the position of the maximum of the locally excited band is polarity dependent. So locally excited band is not polarity dependent. If you see with function of time, it has almost the same value, not change in much value. Then the height of the energy barrier of the excited state is viscosity dependent also. Basically, here they have not studied the viscosity, but sorry, they have studied, but here I do not have the picture of this, but we can just say is based on viscosity. The more viscous is the medium, the more polar will be the excited state. Okay. So in a more viscous medium, you can say that the height of the energy barrier is also dependent on viscosity, or is dependent on viscosity also, and it reduces for a more viscous or a high viscous medium. Here in this graph they have also pasted, I have also attached for just your reference. See, this is the absorption of the system, and this is the emission for the two bands with the polarity in solvents Fa and Fb. So you will note that there is more difference in the value of Fa. What is this Fa? This Fa is the change in the polarity of the change in the polarity of the molecule. So with the change in polarity, the how is the emission with changed with the change in the polarity, for the Fa, how is the emission changed? So in this case you will notice that yes, with the delta F there is very high change in the value of nu bar. And what is this Fa for? Fa is the say the emission or for the A, and FB is for the B1, and therefore it is polarity dependent. So this can also be seen through this graph. Okay. So you, in the first one you will see there is not much change. Okay. But in the second case there are more points which will find out of the line. Now if you have any doubt in this question of DMAPN, just ask, and or else we'll discuss the next question. Okay, we'll go to the next question. That is question number 6. For dimethyl aminobenzonitrile DMABN, the charge transfer band is readily observed in. First is diethyl ether. I can draw the structure of this C2H5. Okay. The next is, this is A option. The second is acetonitrile, that is CH3CN. Option C is the butyl fluoride, that is C4H9Cl. The D one is N-hexane, that is C6H14, right? Now in each of this case, say this is the nonpolar medium. Compared to the other two, this is less polar. This is more polar. And this is the most polar. And thus, since we studied that the value of this charge transfer band, which could be denoted by say this and this as a function of wave number, centimeter inverse, and here it comes to be emission. Okay, so this is the CT band, and this is the uh, say this is the pi to pi star or the emission band A, which is characteristic of the material. So the value of this CT band or this CT band is depends on the polarity of solvent. So it is polarity dependent in this case. Because of this polarity dependence, out of all solvents, charge transfer band appears readily in acetonitrile. Okay. And out of the more the polar the medium is, the better you will see the charge transfer band. Okay. And thus it is most properly observed in this acetonitrile and not in the other ones. Why is the polarity of this? Because there is a long alkyl chain associated with this. In the other cases, it is more or less, it is also not that much polar, or you can say it is also non-polar medium. Okay. So it depends on the polarity of solvent. Okay. And here, what they have given is ET30 is. What is ET30? So basically, ET is a certain parameter. So that depends on the polarity and how with the polarity or the considering the polarity, how the value of K changes for a medium. So the for a betaine dye they had studied which showed which was kept in two medium or the mixture of those which were iso viscous. That is the viscosity of each. That is the viscosity of each was kept or constant, and thus the study of polarity dependence was done. In each case, the polarity dependence or how this polarity dependence is studied, this is studied in terms of the value of ET, which is the micropolarity parameter. The 30 stands for, which is a code given to betaine. Okay. Also, This micropolarity parameter is also affected by or is derived from the absorption of the betaine dye. Okay, so basically the betaine dye it shows an absorption in 300 nanometer around. Okay, and from this we can derive ET, and using this ET value, how does it change with respect? How does this ET change in the medium which is isoviscous? You can just note what is the effect of polarity of the medium, since they kept it to be constant. Why? Because say this is a non-polar and a polar, and this is also a mixture of a polar and a non-polar medium, and this is aprotic and this is protic. And when they studied the two which are isoviscous medium, where one has a aprotic solvent, other one is a protic solvent, the other two are the nonpolar solvents, they could get that how is the hydrogen bonding or the intermolecular polarity, or the say the polarity of the medium affecting the, or is affecting the say the value, or is affecting the, or is useful for studying the solution dynamics. Okay, so just for the information case, this is direct answer. The value of ET30, the ET30 is a micropolarity factor that is derived from the absorption of the betaine dye, which is in the range of 300 nanometer. Okay, and now if you have any doubt in this question, just ask, or else we'll go to the next question. So the difference in the activation energy, the next question is read as: the difference between the activation energies of alcohols and nitriles is equal to energy of a. So when you talk about the activation energies of alcohols and the nitriles, the difference in their activation energies is only because of the one hydrogen bond. This is extra in case of the alcohols, which is not in case of the nitriles. Okay, so if you talk about the alcohol, they have a lot of intermolecular hydrogen bonding in them, while the nitriles lack of that. And if you talk about the activation energy in the two, there is one more barrier in the case of alcohol, that is the hydrogen bonding barrier. And that is why the difference between the activation energy of two is equal to the hydrogen bond between the alcohol hydrogen bonds. Okay. So this is just a theoretical question. In this question, there's like the only difference that is between the two that we can just see and tick the right one. Now we'll go on to the next question, which is: for the molecules with ground states and excited state with different dipole moments, the Stokes shift between the absorption is and emission is greater for. Now, see, earlier we have studied the cases where the ground state is non-polar, the excited state is a polar one. Now, in this case, they have a different dipole moment. Okay. Moreover, say the Stokes shift between the absorption and the emission. Say, what is the Stokes shift? Stokes shift with the term of wavelength, if we study, Stokes shift refers to moving to a higher wavelength order. Okay. Now, say the two are also, they are also in the form of a dipole. Okay. Now here they had represented it in the form like, say this is the, yeah, this is the picture actually. Suppose in this case, the ground state of the molecule has a certain value. Okay. Now, yeah. Um, say this is the case similarly which we have studied earlier also. or which we have been discussing in this session, that say this is for the ground state, this is for the excited state. Okay. Now, for in the case of ground state or excited state, okay, now when the Stoke shift, you talk about the Stoke shift, the excited state due to the solvent interaction becomes more polarized or is more stabilized. Okay. When this is more stabilized, the emission is more red shifted. Okay. Now, pictorially, if you want to draw this, you can just draw it in the sense like, say, okay, I'll just rub it to be more, so that the picture is more clear. Yeah. Say, consider the ground state has certain dipole moment, that is mu g. Okay. By absorption of light, it reaches to an excited state. See this ion H nu reaches to an excited state which has another dipole moment, say mu e. Now, here we have also represented that there are certain solvent molecules around it. Okay. These solvent molecules are the dipoles, say like this. Okay. Plus, minus, plus, minus, plus, minus, plus, minus. Right? What happens as a function of time? Okay, as a function of time, it takes some time, but slowly this excited state, around this excited state, say small e, these dipoles are arranged in an arranged manner like this. Okay. Now say this side of the dipole is a negative charge, so all these have a positive charge towards it. This side is a positive charge, so these are all the negative charge dipoles of the solvent arranged around this. Because of this arrangement, and see, the positive charge is a bit more stabilized by the negative, while the negative of the excited state is also stabilized by this positive. Okay, it's better I just write only one part of it. Okay. Yeah. Say this is the circle, this is the excited state mu e, and what happens is, this is the side. Say this is the negative end. So here the positive ends of the dipole will arrange. Okay. Suppose this is the positive end, and here this side will be the negative end sides of the dipole arrange. Okay. In this whole case scenario, what happens? Say the mu e part or the excited state, it is more stabilized due to the surrounding charges of the solvent. When this is more stabilized, what happens is, it the emission, or say it returns to ground state, from where it returns to further another unorganized state where it has a higher energy, and it reaches to the ground state by emission h nu. Okay. Now, the only factor that affect is, the more is the polarity, The more is the difference in the polarity of the ground state excited state brings the change in the emission and the absorption. If the ground or the excited state is more polar, it is more stabilized by the polar solvent, and if the solvent polarity is more, the excited state is more stabilized. Okay, so the excited state due to solvent interaction becomes more polarized and more stabilized, which brings about the redshift. Soon after, actually, this is the pictorial representation of how from ground state to excited state, which also has a polarity difference. It reaches to some organized state from where, with with some interval of time, it again reaches to a state where these dipoles are unorganized around it, and further from this state it immediately returns to the ground state by emitting certain amount of radiation which has a frequency of nu. Okay, h nu e. Okay, I represent it as h nu e. Basically, what we want to conclude is, the for the ground state and excited state, see, this is the value of absorption. Okay, the more this state will be, okay, I'll just draw it in the form of, say, yeah, now it will be okay. See, it will absorb a certain range, it will emit a certain range. Okay, now because of this effect of the solvent, what happens? Yeah, and this is also non-radiative, only this state is the radiative one. Okay, so this is one with h nu e frequency, and this is h nu a. This is for the absorption. Okay, this is not very clear. I'll write this h nu a. So, because of the polarity, this excited state reaches to a lower energy. Because of this, the value of this h nu e is affected. Okay, this h nu e, the more the difference in the h nu a and h nu e will be, the more will be the Stokes shift. Therefore, the Stokes shift between the absorption and emission will be greater for polar solvents. Okay, so this is the answer. Molecules with a greater excitation dipole moment or a smaller excitation dipole moment. So the more is the dipole moment, the more will be the interaction, the more stabilized the state will be, and the more the more the red shift will occur. Therefore, the molecules with greater excited state dipole moment, this will be the case. Okay. So this is the case only when the mu excited is greater than the dipole moment or of the ground state. Okay. Now, uh, if you have any doubt, just ask, or else we. What I just want to conclude is, talking about the ground state and the excited state and their interaction. If the ground state and excited state both are polar, the excited state, in the excited state, there is some interaction of this excited state with the solvent molecules. As a result of the polarity or the increase in polarity of the solvent, the excited state becomes more stabilized. Because of this stabilization of the excited state, the emission that will occur at a higher wavelength, and thus this is also dependent on the dipole moment of the excited state. The greater the dipole moment, the more the Stokes shift will be, and it is also a function of the polarity of solvents. The For the more polar solvents, the stabilization will be more. Okay. Okay. Now you'll go to the next question, that is question number 10. Solvent response function. See here, we have drawn the same diagram. See, this is a dipole. With the negative end of the molecule dipole, our molecule, the positive part will get attached, while with the positive, the negative part, they form just a sphere. So, to study the solvation dynamics and the experimental approach towards it, what they had done, like, what is the energy with the increase in the say the polarity of the solvent, and when you calculate it with a function of time, you will see, with the function of time, as the time is increased, the emission or the nu or the frequency of the emission with respect to time, it becomes more, oh sorry, it becomes lower, or the uh, yeah, it becomes lower, and therefore a redshift in the emission occurs. Okay. Now here they have pictorially represented it, as we have included a diagram for the illustration. Say this is the S0 or the ground state. This is the S1 state, the excited state. With the function of time, what happens as the time is increased, this, and with the arrangement of these molecules around this our molecule, slowly there is stabilization in the excited state, which brings about that the ground state becomes more stabilized, and therefore the emission in the last case will occur at a lower frequency or a higher wavelength, lower frequency or a higher wavelength. So, simply for any molecule which is polar, and first of all, which is polar, and which is affected, how it is affected by the solvents, there was a solvent response function, which can be developed by the time dependent Stokes shift study. In this stock shift study, what happens, they consider the value of nu t, nu infinity, nu zero, and nu infinity again. So nu t is with respect to time, what is the value of the emission frequency. Okay, so in this case, say this is the emission frequency, so nu, this we can say this is the nu 3. Okay, why? Because it is at lower energy, and the nu is directly proportional to t. And then in terms of energy, this is nu 2 and this is nu 1. Okay, here I denote it with nu 1 at a higher arrow. And if you study it with respect to time, say nu 1, say for 1 it is the highest time. No, not the highest, the lowest time. For the nu it is the highest time, nu 3 it is the highest time. With increase in time, the value of t reduces. Infinity refers to when the total solvation occurs. Solvation refers to when the molecule is just surrounded by or just covered homogeneously by the solvent molecules. Then V is equals to 0 is the emission wavelength, or sorry, emission frequency at the time 0. And nu is equals to infinity is the emission wavelength at time anytime uh, higher, beyond which solvation has occurred, or after the solvation. Okay, so the equation for this can be written as Vt minus V infinity upon V0 minus V infinity. Basically, for this Vt as a function of time, or sorry, V infinity, yeah, you can also say that uh, if this V infinity should be almost equal to or lower than that of the Vt. If it is not, or the time at which the infinity or the solvation occurs totally, that should be lower than what we are, the time at what we are studying our process, or we are undergoing or studying the solvation dynamics process. Okay, so solvent response function, which is denoted by ct, the value of Ct is calculated by this value V0 minus V infinity upon V0 minus infinity. Okay, and this V is not V, actually it is nu. Nu is symbol for frequency. Okay, and what is this frequency? This is frequency is the emission frequency. This, from this potential well diagram, you can see that in the potential, the with the function of time, the excited state, it becomes stabilized because of this solvation interaction or the interaction with the solvent. This interaction of solvent is also function of polarity of the solvent, and that is why this is called a solvent response function. So this varies with the variety of solvent, varies with the variety of solving. Okay. Now, so far we have discussed 10 questions. Uh, we have some time left. If you have any doubt in any of these questions, you can ask, or else we'll just take a quick watch on all the questions once again. The first question was, what are the excited state processes, and in the excited state processes, how do the things happen? So in the excited state processes, first, because of the excited state, or say more polarity, or the polarity dependence of the excited state, which is itself a dipolar or state, then in this case, the fluorescence emission, because of the polarity, the state will be more stabilized, and therefore the fluorescence emission that occurs will be redshifted a lot. Then since there since the excited state is comparatively stabilized, there will not be a good overlap between, like, the fluorescence spectra will differ from that of the absorption. Second thing, here we had studied it through a graph or a spectra, where you can see that the fluorescence intensity for the excited state, it is denoted by these two, where the B stands for the another uh, emission that is accompanied by another, or the uh, second or the higher wavelength emission, that corresponds to the excited state process. And in this case, if the excited state is a polar enough, and it is polar, and it undergoes different processes, then in this case, for the second peak, the decay which you will note, it will give a rise with time, and the decay, the first decay will show a decrease, or will show a faster decay, why? Because most of the population which used to be only in the state A is now distributed to A and B, and therefore the molecule the uh, most of the molecules which are in the system A will then decay faster. Okay. Then, based on the E-ring equation, we also calculate the time constant, that is T. And here we discussed what the T is, how sorry, what the T is. The T time constant is the inverse of the rate constant. When you calculate it, you just consider for the fastest process the activation energy is 0, and then you go on for the next question 3. In the experiments of Zwill, the bond breaking time and the period of oscillation for the bond dissociation. Here they studied two systems. This was the earlier one, was the simplest system of ICN, where the photo dissociation is used done by the pump probe experiment itself. In this, the pump was one with the 306 nanometer light, which used to excite the system to a higher state. In this excited state itself, it is incident with another frequencies of 388 nanometer, that is the probe, which then helps in dissociation of I and Cn. The Cn then dissociates and reaches to a higher energy. The most of the Cn minus, that is the system, reaches to a higher energy, where the Cn minus is the one in the excited state. This Cn minus, when it comes to the back to the ground state, it is responsible for the fluorescence emission. When you record this fluorescence emission as a function of time, you will note that at time 0 there is no intensity for this emission, but with the function of time, or when the time is increased, as the time increases, it reaches to a it the intensity of the emission or the fluorescence emission increases, which then becomes constant. When you just take or calculate the time it has taken to reach a maximum possible value, you can calculate the so-called, what is the dissociation time, or the time it takes to dissociate, or the bond breaking time. Similarly, in this case, the snapshots of bond breaking for NAI, we had studied that the NAI, which is ionic in nature, by absorbing certain amount of light, it reaches to the excited state. Now, it so happens that the two states, or the overlap to each other, that is the Na plus, the excited state of Na plus and Na. As a result of this, some amount of Na plus is converted to Na. When this is converted to Na, you will see that there will be two absorption. The first will be of Na plus, and the second will be of Na itself, and or the free Na. What so happens is, during the breaking of this bond, this is not a single level. There are many small levels within this. Therefore, each emission or the transition is not accompanied by a single wavelength. It is a spectrum, or it is a bunch, or it is a bundle of different wavelengths. Therefore they call it to be as a wave packet. Okay. Now in when this bond breaking occurs, the absorption of free Na with the function of time is not constant, or is not increasing and just becoming constant. It is in the form of, say, oscillations, which indicates that during the bond breaking, there the wave packet, it oscillates between two states. First is the bonded state, and the second is the unbonded state, or where the bond is broken. And with the time, when further what happens, slowly this bond breaks with the function of time, and therefore slowly you will see that the intensity of the Na plus absorption has reduced. Okay. And then we move to the so therefore the answer for this question was that the bond breaking time that was calculated is 205 femtoseconds, and the period of oscillations which was noted from the difference in these two was calculated to be 1 picosecond. Okay. Now, regarding the mechanism of acid base through pump probes with the high concentration of the solvent molecules leads to. So, for this, they had studied, this was an experiment which was done by Nibbering and group, where they had studied in detail about how the acid base reaction takes place. The whole process was also studied through the ultrafast process study only. Why? Because the acid base reaction is considered to be as one of the fastest reactions. When they studied that, they took pyranine as the photoacid and acetic acid or the acetate ion as the solvent medium or the medium. Now, when they considered for the higher concentration of the CH3CO minus, what happened is the two photo base and CH3CO minus, their intensity increase with the time was almost same. Why? Because whenever the photo base is formed by release of D plus ion, immediately the D plus reaches through CH3CO minus to form CH3COD. Therefore, their intensity does not have much time difference. But at the lower concentration, we observe that there is a difference which is a function of time. Why? Because the acetic acid concentration does not increase with time as it increased in case of high concentration, since in a medium there can be some time lag due to some intermolecular interaction for the D plus to reach to the acetate anion. Therefore, when the solvent concentration is high, that is the acetate concentration is high, there will be increase in the rate of reaction. While when the acetate concentration is low, there will be like the rate of reaction will be comparatively less. Okay. Now, next was the diaminobenzonitrile. This is one of the example which shows the TICT, that is the twisted intramolecular charge transfer. We also studied that in this case, as the polarity of the solvent increase, the charge transfer, its rate increases or not increases. The twisted intramolecular charge transfer happens, which gives a Stokes shifted emission band, which is also polarity dependent and viscosity dependent. Further, we studied in the next question, the charge transfer band is readily observed. So, as I said, for the charge transfer band to happen, the medium should be quite polar. Therefore, in case of acetonitrile, you will observe the charge transfer band. Then we studied what is ET. So ET is a micropolarity parameter which is used to study how the polarity dependence happens to be in any dye. So for this they had taken betaine dye which absorbs in the 300 nanometer. In order to calculate this ET, which was calculated or which was derived using the absorption or the value of absorbance of the betaine dye. Thus, the answer to this was the ET30 is a micropolarity parameter, and which depends on the absorption also of the betaine dye. Then we studied how is the difference in the activation energy of acetonite alcohol and nitriles bond. That is the energy difference in the activation energy is equal to the value of the energy of a hydrogen bond. Then we also studied how in the ground state and excited state the dipole moment of the polar or the polarity of the solvent, it affects uh, the emission and absorption. So we noted that as the if the excited state is quite polar enough and the medium is also polar, then in case of polar solvent it will show red emission. Also, if the excited state is itself polar enough, then the emission will be in the red shifted region, and therefore you will observe more shift. That is, shift is the difference in the nu of E, nu of A minus nu of E. That is the Stokes shift, they say. Then, based on the polarity of the solvent, there is a function which is derived called the solvent response function, which measures how is the change in the emission of any particular system happens as a function of time, depending on the polarity of the solvent, which is called as the solvent response function. So therefore we measure with respect to time what is the change in the emission wavelength or frequency, and thus we calculate the so called CT. Okay, so in this week 9 we have discussed 10 questions. There are few more questions that are remaining from the assignments, which we'll cover in the next in the next session. Okay, session 10. So thank you so much for joining the session. Now we'll end the session. Uh, okay.